This is going to be a follow-up video to the one I did previously on the normal curve. So I'm just going to go over a quick overview of what we talked about last time, or what I talked about last time. If you take a large sample of the population and say administer a standardized test such as an IQ test, and then you graph the frequencies, you'll come up with what is called a bell-shaped curve, like I have here in this picture, called the normal curve. Also, you might have a normal distribution if you take measure the life of a certain light bulb, for example, and plot the information. You could get, in some cases, a normal curve also. And the thing about the normal curve is these percentages that I have here are pretty much fixed. Remember we talked about this middle value here, mu, is representing the mean, and then the sigma is the standard deviation. So I go 1 standard deviation above the mean, and then 2 over here to this value, and then over here 3, and then we go below the mean, mu minus sigma, 1 standard deviation below, and then mu minus 2 sigma, 2 standard deviations below, and so forth. And then you notice the percentages. Now you can think of these percentages also as probabilities. So I can express this 34.1 as 0.341 and so forth. If I add up these percentages, I get 100%. If I'm thinking about probability and I add these as a decimal, I get approximately 1. Okay, in theory anyway. Because remember, this curve approaches the horizontal axis as the values go to infinity, and over here on the left side also. I also can think of this area, this section under the curve. All of this, we can talk about the area under the curve. So we can talk about the percentages, we can talk about probability, and so forth. Now, to compute problems involving the normal curve and finding probabilities, we need what I call the z-values that I talked about last time. So in certain situations, then you're given certain data, and then to compute probabilities, you'll need the z-values. And remember, to find the z-values, you subtract the mean from the value and then divide by the standard deviation. So this would be, in this case, mu minus mu is 0 divided by the standard deviation would be 0. So this mu would be a 0. And then the next one is if I subtract the mean and divide by the standard deviation, I would get 1, and then I would get a 2 and a 3. On the left side, I would get a -1, a -2, and a -3, and so on, in terms of what we call standard scores. Okay, I would get the standard normal curve. So for example, last time we looked at the normal curve in terms of IQ scores. So we said the mean of a certain test is 100, the standard deviation is 15. So if I plot that, I will get something like this. Okay, 100, 115 would be 1 standard deviation above the mean, 130 would be 2 standard deviations above the mean. Standard deviation here is 15 for this particular test. 85, 1 standard deviation below. 70, 2 standard deviations below the mean. So if the mean is, or the z-value is positive, then we're above the mean. If the z-value is negative, then we're below the mean. Okay, so 115 is 1 standard deviation above the mean. 85 is 1 standard deviation below. Notice this percentage is still the same. This was approximately 0.34 or 34% on this side here, 34%. So this is saying, okay, the value from -1 to 1 standard deviation is 68%. Those are all going to be fixed. Okay. Now, when we're finding probabilities, the problem is the z-value, or the standard score, is not always going to be an integer. So we have to be able to compute these. Now let me just show you that if I go ahead and subtract the mean and divide by the standard deviation, then I would get something like this. Okay. So instead of 100 here, I have the 0. That represents the mean. Okay. And then over here, instead of 115, I have 1.
and then 2 and 3, and then 1 standard deviation below, -1, -2, 2 standard deviations below, -3, 3 standard deviations below. Notice that these values still stay fixed. Instead of 34.13%, I'll have it as a decimal between 0 and 1. So again, these values could represent probabilities if that's what we're looking for. They could represent percent of the frequency in a certain interval. They can represent area under the curve. Depends on what they ask you for. Okay, so last time we were looking at finding the percent between two z-values. So I went through these problems right here. This is what I did in the last video. Find the percent of the total population that is found between the two given z-values. The first one was the mean and 1.4. So this would be 0 and this value then 1.4 positive. So the z is over here. The next one was the mean and negative 2.22. The z-value is negative, so that would be on the left side over here. Okay. And then the next one between negative 1.4 and 1.4, so it would be 1 on the left and 1 on the right. And we talked about the symmetry. So if the z-value is negative, we said you can ignore it and just look up the positive one, and that's the same answer. Okay. So the answer to number 3 then, since we've done number 1 from 0 to 1.4 was 0.4192. So we said, okay, this is just going to be double the area, or in this case the percent, and we got 0.8384, or in this case 83.84%, because they're asking for percent. Okay, so if you have a situation and you want the percent, or you want the probability between 0 and a z-value of z2, which is over here, we simply look up this value in the table. The table, let me go back to the table here. So remember, the table gives you the value from the mean to the z-value. So if you want the area or the percent or the probability between the mean and 0, between the mean and 0.1, then you find 0.1 under the z-value, and you look to the right, you notice it's 0.00, so the answer in that case would be 0.0398. That would be a probability of 0.0398, if that's what they're asking you for. Or if they're asking you for a percent, it'd be 3.98%. Now, if you wanted the percent or the area or the probability between the mean and say 0.11, then you'd have to go to the second column over here. So 0.1, and then you go over to the 1, and you'd have 0.0438 probability, or 4.38%. Okay, that's the way the table works. So again, if it's negative, you can ignore the negative, because of the symmetry, it's going to give you the same value. Okay. So let's look at the first problem then. Suppose that people's heights in centimeters are normally distributed. That means it's going to form a normal curve with a mean of 170 and a standard deviation of 5. We find the heights of 1,000 people. How many would you expect to be between 165 and 175? Okay, so the mean is 170, so that's about 5 feet 7 inches, something like that. Okay, approximately. In this case, it's in centimeters. How many would you expect to be between 165 and 175? So notice in this case, the 165 is to the left of the mean and the 175 is to the right. So you have a situation like this, Z1 and Z2. So what you would do in this case is you simply find the value, this area in here between 0 and Z2, and then the area between 0 and Z1. And then because it's all of this, you would add those values up. Okay. So first though, now in the ones that I did last time, you were given the value as a z-value. Okay, in this case we're not given the v-value, so you have to compute it using this formula. Okay, if x is a value from a distribution with mean x bar and standard deviation s, you find the z-value or the z-score or the standard score, different names for it, by computing this. Subtract the mean from the value and then divide by the standard deviation. Okay, so in this one we take 165, subtract the mean, which is 170, divide by 5, we get -1. And then for the second one, 175, subtract the mean, 170, it's 5, divided by 5, we get 1. So then we want the value between -1 and 1. Okay, and of course that one we saw from the standard curve was 0.3413. If we look at the table, go to 1, and there it is, 1.0, so we look to the right, 0.3413. So because it's the same value, or 1 and on the opposite side, because of the symmetry, you just double it. Okay, so 0.3413, I double it and I get 0.6826. So the percent or the probability of a person selected at random being between those two heights is 0.6826. Now they want to know how many we would expect to be in that interval. So in this case, we take the 68.26%, convert it to a decimal, which is of course the probability, multiplied by 1,000, and we get 682.6, and I just rounded that off. So this is approximately equal to 683, rounded off. Okay. Now with the next one, how many would you expect to be taller than 168? Taller than 168. Okay, so we take the 168, subtract the mean, 170 divided by 5, we get a -0.4. Okay, so we go to the table, and again, ignore the negative, so just look at 0.4, and then to the right we had 0.1554. There it is. So again, if you look at your z-value, so in this case we had just one z-value right here, so that 0.1554 would be this right here. So then we want this plus everything over here, right? Because it says how many would you expect to be taller. So we'd have to add the 0.1554 because that's the value from the mean to from the z-value to the mean, I should say. And then to the right of the 0 or the mean is another 50% or 0.5. So we add that to that and we get 0.6554. Okay, so that's the percent. So the number we would expect would be 0.6554 times 1,000. Again, rounded off to 655. So 655 would be taller than 168. Okay. What is the probability that a person selected at random is shorter than 171? Shorter than 171. So first we, again, in this case, we have to find the standard score or the z-value. So take 171, subtract 70, divide by 5, we get 0.2. So again, in the table, we go to 0.2, and we find 0.0793. 0.0793. So shorter than that. Okay, so again, if I go to the table, this z-value is right here to the right. Okay, so the table, the value from the table is this right here between 0 and z2,
And we want shorter, so that means it has to include everything over here. So it has to include that value from the table plus everything on the left of the mean. But that's 50% of the area, or 0.5. So in this case then, I would simply add the 0.5 to the 0.0793, and I get 0.5793. So in this case, it's asking for the probability. What is the probability that a person selected at random is shorter than 171? So I would just give the answer as 0.5793. The probability is 0.5793. And of course, in Part D, I simply use the information from Part C. It says, how many of the 1,000 persons would you expect to be shorter than 171 centimeters? Well, in that case, I just multiply that by 1,000, and I get 579.3. I'll round that out to 579. There it is. Okay, so we've talked about IQ scores already and so forth. This is an example of that. On standard IQ test, the mean is 100 with a standard deviation of 15. The results come very close to fitting a normal curve. Suppose an IQ test is given to a very large group of people. Find the percent of people whose IQ scores fall into the following categories. Less than 100. Okay, well, the z-value for 100 would be 100 minus 100 divided by 15 is 0. Okay, so less than 100 would simply be everything to the left of the mean, and you notice the curve is 0.50 and 0.50 on each side, or 50% and 50% on each side. So if it's less than the 100, or in this case the z-value of 0, that would be 50%. 50%. Okay. Now, greater than 145. Greater than 145. So we want to know, find the percent of those that would have an IQ of higher or greater than 145. That's a high IQ. So that would be the geniuses, okay? So we would look up 145 minus 100 divided by 15. We get 3. Okay, so then we would go to the table, and then 3, we have it there, 3.0, so it would be the first column, 0.4987. 0.4987. Okay. So if we look at this, let's say that Z3 represents that value of 3. So we want everything right in here. How much area or percent is this over here? Well, we know that from 0 or the mean to right, all the way to the right, that's 50%. So we just want this little portion right there. We simply would subtract that from 50% or the 0.5, depending on how you have it written. So in this case, I would have the 0.5 minus the 0.4987, and I would get 0.0013. Since once the answer is a percent, I would move the decimal over 2 places and then stick my percent sign. So that would be 0.13%. Okay, so that's a small amount of the population. Like I said, those would be the geniuses. So 0.13% is what we would expect to be higher than 145. Okay, between 70 and 130. Between 70 and 130. So we know, okay, how many would have, we would expect to have an IQ between 70 and 130. So we find again the z-values for each one. 70 minus 100 minus 30 divided by 15, that's negative 2. And then 130 minus 100, that's positive 30 divided by 15, that's 2. Okay, so we look up the 2 in the table, okay, and we get this value right here.
0.4772. 0.4772. And because of the symmetry again, because we want everything between -2 and 2, we just double this. So that's 0.9544. And then convert that to a percent because it wants a percent. So that would be 95%. Round it off there. Okay. Now if it's asking for how many would you expect to have a probability, or what's the probability that a person selected at random would have an IQ between 70 and 130, then in that case you would say the probability is 0.9544. In this case it wants a percent, so I just round it out to 95%. Okay, in the next one, it says a certain light bulb has an average life of 600 hours. Okay, with a standard deviation of 50 hours. The length of the light bulb can be closely approximated by a normal curve. Okay, so when it tells you something like that, then you know you can apply this method that I'm using right now, if you know it's approximated by a normal curve. So a warehouse manager buys and installs 10,000 such bulbs. Find the total number that can be expected to last the following amounts of time. So in this case, we want the total number. So basically what we're going to do is just find the percent that would fall in that particular category, and then just multiply it by the number installed, which is 10,000. Okay. So say at least 600 hours. You want to know how many we would expect to last at least 600 hours. Well, again, 600 hours, remember, that's the mean. So that would be right in the center. That would be your 0. So to the right, that's 50%. Okay? So 50% would be expected to last the 600 hours. So 50% of 10,000 is 5,000. So the answer is 5,000. Okay. Now, how many would we expect to last between 600 and 675? Okay, so again, we find the mean for these, the z value. So 600 minus 600 divided by the standard deviation, which is 50, would give me 0. And then 675 divided by or 675 minus 600, I should say, divided by the standard deviation of 50 gives me 1.5. So in the table then I would look up, because it's between 0 and 1.5, I would just look up the 1.5. Okay. Look up 1.5. And I see 0.4332. 0.4332. Okay. So then we would just multiply this 0.4332 by 10,000, and the amount of bulbs would be 4,332. Okay, 0.4332 is a probability, or the percent. If you look at that as a percent, so multiply by 10,000, we get 4332. Okay, how many would you expect to last less than 740 hours? Less than 740 hours. Well, again, we find the z value, so 740 minus 600 divided by 50, we'll get 2.8. Get 2.8. So we go to the table, look up 2.8. There it is. First column, since it has the next digit is 0. 2.80 you want 0.4974. Okay, so because we want everything to the left of that, okay, we have to take the 0.4974 that goes all the way to the mean of 0, and then to the left of that is 0.5, or the other 50%. So we add the 0.5 to that, and we get 0.9974. 0.9974. Multiply that by 10,000, just move the decimal over 4 places, and the total number that would last less than 740 hours would be 9,974. Okay. Okay, that concludes this video. Again, if I went kind of fast through this, just rewind and pause it if you want. On the next video, or part 3, I'm going to go over basically these same problems, but instead of using the table, I'm going to use the graphing calculator, and the one I'll be using will be the TI-83. So if you're interested in that, please be ready for that video. And again, as usual, have any questions, please post them. Any suggestions, again. And again, if these are helping you, please subscribe to the channel, and we'll see you in the next video.